and welcome to our Flavonoid Identification tutorial. Flavonoids are a diverse set of polyphenolic compounds produced by plants that are crucially important to both plant metabolism and potentially human health. These compounds have demonstrated anti-inflammatory, anti-cancer, anti-diabetic, anti-aging, and even neuroprotective effects, and understandably have garnered a lot of interest as potential therapeutics. There are thousands of flavonoids in nature, most of which have never been purified or structurally elucidated. This can pose a challenge when trying to identify novel flavonoids, as you can't rely on traditional library annotation. However, we can use a combination of molecular networking and the mass spec query language, or MassQL, to rapidly identify flavonoids in mass spectrometry data without prior knowledge of their exact chemical structures. So let's get started. Today, I'm going to be analyzing MS data from 4 plant species. While I could run MassQL directly on these files, instead, I'm going to begin by running molecular networking. To start a molecular networking analysis, go to the Workflows tab, and then find Molecular Networking. For a detailed tutorial on how to run a molecular network, I highly recommend jumping over to our Running Your First Molecular Network tutorial, which goes into this workflow in a lot more detail. But for today, all we're going to do is choose the MZ-XML files containing our MS data, and then scroll down to the bottom and click Submit Workflow. So that task took about 11 minutes to complete, and now we can check out our results. The first thing I like to do is go to the Library Identifications table. Here you'll see that we already have some library matches to flavonoids, which is great to see. Now we can go to our molecular network to see how they map together. To do so, click on the Visualize Full Network in Browser, which will pull up the entire molecular network. In a molecular network, each circle or node represents a different metabolite. Metabolites that have library matches are shown in blue, while those that don't have library matches are shown in gray. An edge between 2 nodes indicates that those compounds are structurally similar. Molecular networks organize themselves into subnetworks, which tend to correspond to specific compound classes, like flavonoids. We can zoom in on one of these subnetworks by entering the number 15 in the component filter here. This will highlight a subnetwork which already has library matches to several known flavonoids. You can compare those known flavonoids to related unknown compounds by simply clicking on the edge between 2 nodes. This will pull up the MS2 spectra for each compound and allow you to compare between the two. So you can see these 2 spectra are very similar, which indicates that this unknown molecule is likely some sort of flavonoid and is thus already an excellent candidate for further study. While this is a great start, not all novel flavonoids will be linked to known flavonoids in a molecular network. This is especially true if that novel flavonoid has a lot of modifications on the flavonoid core. So we're going to go a step further and use MassQL to search for other compounds that might have been missed by molecular networking. To do so, we're going to search for 3 diagnostic fragments that are common to many flavonoids. The first is a fragment at 303.05 m/z, which corresponds to the core structure of quercetin, and the second are 2 fragments that are created when the flavonoid's core structure breaks down in the mass spectrometer. Now, if you've never run MassQL before, feel free to jump over to our MassQL tutorial where we go into this in more detail, but for now I'm just going to pull up the translation of one of these queries. Basically, we're asking the algorithm to return MS2 spectra that contain an MS2 peak at 303.05 m/z with a mass tolerance of 0.05 m/z and a minimum intensity of 5%. We're going to write a separate query for each of our diagnostic fragments and then combine them by adding these 3 horizontal lines between them. This will look for all 3 queries separately, but if you want to look for a spectra that contains all 3 of these MS2 peaks, you can instead combine the queries with the terms and or. Of course, these 3 peaks aren't the only diagnostic peaks for flavonoids, and it's very easy to change MassQL queries to look for whatever spectral feature you're interested in. For example, if you want to look for camphorol at 267.05 m/z, you can just switch out the search parameters in that MS2 prod section to get this query. MassQL can also search MS1 peaks, retention times, charges, peak intensity ratios, neutral losses, and the list goes on. To run MassQL on our molecular network, I'm simply going to go to my molecular networking task page, scroll down to Downstream Analysis, and click on MassQL Query. This will open up a new analysis with all the correct input files already selected. All I need to do is copy-paste that query into this box and click Submit. So this analysis only took about 13 seconds and returned 49 spectra that matched to at least one of our queries. To check out the matches, you can click on this query list here, which lists out every spectra that matched our search parameters, or you can click on Visualize Full Network in Browser to overlay the MassQL hits on the molecular network. The easiest way to do this is to change the node size option here to Enriched Query Index 0. This will highlight matches to our first query, which was that MS2 peak at 303.05 m/z. You can also choose Enriched Query Index 1 or Enriched Query Index 2 to visualize matches to the two other queries. What's nice to see here is that while many of the MassQL hits are compounds that already have library matches to flavonoids, we also have hits for unknown compounds, including compounds that didn't network with our known flavonoids. We also see that each of our queries identified a different population of metabolites, which likely means they're finding different classes of flavonoids, and that searching for all of these 3 queries is giving us a more comprehensive list of potential flavonoids in these samples. So what we've done today is rapidly identify many known and unknown flavonoids in plant samples. This process took MSMS files without any pre-processing and performed spectral clustering, library matching, peak integration, molecular networking, and MassQL in less than 15 minutes. This type of analysis speed allows you to rapidly search and refine queries for whatever class of compound you're interested in. Thanks for watching.